Good morning, everyone. I would like to begin with the section one.
Yeah.
Professor Mario Di Stefano is the chair of this session, and I will be the co-chair. My name is Ana Simões from Instituto Superior Te in Portugal. So, Professor Mario Di Stefano, if you would like to introduce the speakers, please.
Yes. So, Anna, thank you. I rely on your help to conduct this session. And anyway, so actually, this session, four papers will be presented and dealing basically with reinforced concrete structures. So I think that this session is placed correctly and appropriately after the very interesting keynote lecture given by Professor Umberto Varum. So let's start with the first paper entitled Seismic Enforced Displacement-Based Pushover Analysis on Irregular In-Plan RC Multi-Story Buildings. The paper will be presented by Triantafyllos Makarios of the Aristotle University of Thessaloniki. So please, Professor Makarios, go ahead.
Thank you, Professor Mario. Ladies and gentlemen, the present paper has titled Seismic Enforced Displacement-Based Pushover Analysis on Irregular In-Plan RC Multi-Story Buildings. Okay. The shortcomings of nonlinear static pushover analysis on asymmetric multi-story buildings. It is well known that the various forms of nonlinear static analysis, namely pushover analysis, have many shortcomings. Several of them are inability to rational estimate of the dynamic coupling of torsional with translational oscillation of the floor diaphragms. 2. Inability to rational estimate of the action of the higher mode effects. 3. Forbidden superposition in nonlinear area to consider the spatial seismic action. Unclear definition of an appropriate principal reference system in the nonlinear area for the documented application of the pushover procedures. And inability to verify the torsional sensitivity of the nonlinear model of irregular in the plan buildings. The basic concept of the proposal is the capable near collapse principal system of the building is defined as the appropriate nonlinear principal reference system. Seismic and elastic floor enforced displacements are applied on each floor diaphragm at the location of the vertical ideal principal axis. In this way, the building is driven directly to the near collapse state. In other words, our methodology is a direct displacement-based procedure. Avoidance of various superpositions using suitable floor-enforced displacement in each floor to fully consider the spatial seismic action via 16 pushovers, where the envelope of these 16 pushovers is considered as an estimation of the seismic demand. In other words, the seismic action is taking account as suitable floor-enforced displacements. Please change. I have a problem. I have a problem to change. Yes. No. Can't you share my desktop, please? To change.
Sorry to interrupt. You have the full control of the presentation. If you just put the direction up and down.
I can't go to back.
Okay, go back. Okay, I will ask to go back on your presentation. Like this is okay?
Go back. Go back, please. Okay. In the present methodology, here is the center mass of here. At the capable near, here the capable near collapse center of stiffness, here. At I axis, at 2 axis, the ideal principal horizontal axis of the building. We are giving 100% of enforced translation along the first axis, and simultaneously we are giving a 30% along the 2 axes, the other horizontal axis, and simultaneously we are giving a floor rotation about the ideal vertical axis is past this point. We take thus we take the spatial seismic action with alteration of signs and between ratios. 16 combinations of enforced displacement have been arisen. Please go. The proposed the proposed displacement base. The main steps are the nonlinear model of the multi-story building is formed by assigned to the structural members with their second stiffness of yield in order to simulate the extreme capable near collapse state according to Eurocode. Calculation of the vertical fictitious elastic axis, namely the optimum torsional axis of the above-mentioned multi-story model of building. Thus, the location of the capable near collapse center of stiffness of the multi-story building is the point of the diaphragm at 80% of building height from its base, from which the optimum torsional axis of building is passed. Also, the orientation of the horizontal capable near collapse principal axis 1 and 2 of the multi-story building show the landing principal directions of the building with lateral floor static forces. Moreover, the capable near collapse torsion radii of the multi-story buildings shows the torsional sensitivity of the building into the nonlinear area using this relation scheme. In order to estimate the suitable floor enforced displacement, we use two different sources in between combinations. According to the first source, by this diagram, by extensive parametric analysis using nonlinear response history analysis, two floor translation along the horizontal ideal principal axis 1 and 2 are estimated via the final anelastic floor angular deformation for each level. In other words, it is the drift ratios of each floor divided by each floor height. In the picture, we can see that knowing a level, we can estimate the anelastic floor angular deformation at near collapse state for frame buildings, wall buildings, and dual buildings, and for each static eccentricity and torsional flexion of or stiff system. Please go go back. By the same way, moreover, from figure 2, we can directly take the floor and force rotation about an ideal vertical axis. For 3 building types, frame buildings, wall buildings, and dual buildings. According to the second source of the floor and force displacement, we must carry out 2 sets of temporary pushover analysis, with the floor lateral forces acting on the vertical 3 axes along the horizontal axis 1 and 2. In the first set, the lateral floor forces following the uncoupled fundamental translational mode shape, and in the second set, the 80% of the base shear is distributed as in the first set, and the rest to 80% of the base shear is located as the concentrated lateral force at the top of the building. Note that the considered of 2 signs, positive and negative, of above mentioned loading vectors, thus 8 temporary pushover analyses are performed. Here, P delta effects are included, and the target displacement of the top of the 3 axes is calculated by the table 1. The final envelope of the floor angular deformation is taken from the envelope of the 2 sets of temporary pushovers and from the proposed values of figures 1 and 2 by parametric analysis. To consider the spacing seismic action, 16 appropriate combinations of the floor and force displacement are formed, where we must take their envelope in the seismic demand at the near collapse state. Afterwards, all the above mentioned are true with very accuracy on the near collapse state of the building. For the other seismic performance levels, the present methodology is scaled down according to this guidance. Please go back. Also, we can see a short numerical example. We can see a plan of an asymmetric 5th-story building that is designed by Eurocode 8. We can see the center of mass, as well as the center of stiffness in the near collapse state, and the ideal horizontal axis 1 and axis 2. By the first source, by nonlinear response history analysis, namely figures 1 and 2, we get the angular deformation in elevation. By the 2 sets of temporary pushover analysis, getting deformation in elevation, and in the final 16 pushovers with simultaneous combination of enforced displacement. The results with a dotted line is the results of by nonlinear response history analysis, and with continuous line is our methodology. We can see the floor displacements, first floor, second floor, third floor, fifth floor, for I direction and for 2 direction. So we can see that a very good accuracy by the proposed methodology. Also, the floor angular deformation along 2 axes and along 1 axis, giving very accuracy. And a comparison with other types of pushovers extended N2 and the simple N2 pushover procedure, where the same conclusion is it is. The accuracy is very good. The capacity curves. The conclusions. Using the present methodology, the seismic action is taken account with suitable floor and force displacement. Given by figures 1 and 2, we can directly calculate the final floor displacement at near collapse state. Superpositions don't use for spatial seismic action in the present methodology. The floor inelastic torsion is estimated with very good accuracy. The new procedure is very simple for all engineers. The basic key of the definition of the capable near collapse principal system, that is the fictitious elastic system of multi-story building at the near collapse state. Thank you for attention.
Thank you, Professor Makarios. I don't see any request.
Yes, there's no questions from the.
There are no questions, so you confirm me there are no questions. So I make one question, but very short one. So you plan to check your method also for torsionally stiff systems, because you checked for torsionally flexible systems, but you plan to do it also for torsionally stiff and very torsionally stiff systems, such as those having shear walls at the perimeter.
Thank you for your question. Yes, yes. We are check all types of buildings at torsional flexibility and stiff torsion.
Thanks. So if there are no more questions,
And I'm sorry. And,
no.
this is an abstract by the full paper is before 3 days by published by Generic Structural Journal.
Okay. Thanks for your presentation, and we go to the next one. Paper is entitled Design Approach for an Irregular Hospital Building in Bucharest, and will be presented by Professor Dietlinde. So it's an occasion also to thank Dietlinde for having organized the past Bucharest workshop. And okay, so please, Dietlinde, go ahead.
Thank you also. It's nice to meet you all again on this occasion. Unfortunately, not how we wanted to. I hope everyone can hear me. Is it okay? Yes? Thanks. So I would like to present to you today some issues regarding the design approach for hospital building in Bucharest. And first of all, I want to explain some ideas about the aim of the study. Why Bucharest and why a hospital building? First of all, for Athanasios. Why Bucharest? Because the entire southern part of Romania, to which Bucharest also, where Bucharest also is situated, is has a very weak ground, a very weak foundation ground. We have many rivers that pass through the southern part of Romania from the mountains to the Black Sea. And so we have irregular ground, foundation ground. This gives us really high corner periods. And on the left side of this slide, you may see one of the response spectra from the national seismic code from Romania. And you see, for this one, we have corner periods up to 1.6 seconds, and this is quite high. Actually, according to my knowledge, such high values of corner periods fit only the Mexico City area, but the Mexico City area has also bright band seismic registration. We in Bucharest, from the Vrancea seismic source, don't have bright band motions. We have pulse type motions, and you can see here on the right side of this slide one example from 1977 from our biggest earthquake recorded till now. Yeah, it was an earthquake at 7.4 magnitude Richter scala value. So it means actually we have quite a huge amount of energy from earthquake that is gets free in a very short time period and affects, especially in such regions with high corner periods, the flexible structures. The idea was to see under those special seismic conditions if base isolation as maybe an appropriate way of coming along with the seismic action, especially also for flat and elevation irregular structures. So actually, we have chosen a hospital building due to the fact that especially for hospital buildings we expect and we want to have immediate occupancy. Yeah? We want the hospital to be operational, to remain operational after a strong seismic event. Under the seismic conditions of Bucharest area, we have actually displacement amounts of 40 centimeters. And if we think about the fact that, for example, for pushover analysis, yeah, we are requested by the seismic codes to reach out with the displacement capacity of our structure until 1.5, this value will come to 60 centimeters, which is a lot. On the other hand, base isolation in Romania is at its start for civil structures. It was used quite large in a large area for bridges, but for civil structures, actually not. Just few cultural and historical monuments were considered to be retrofitted by this method till now. So the confidence from practical engineers for this method needs a little bit more help. The hospital structure we have chosen is a hospital structure which is already built in Bucharest. It was built according to the former version of our national seismic code, but in 2012, so it's not an old structure. It's a reinforced concrete structure which has, in a plan view, quite overall frames, except the southern part where we have an elevator shaft. The right part, the right 3D view of this structure shows you a structure with reinforced concrete walls on the outside, but those walls are actually not reinforced concrete walls, they are non-structural walls. And we have used this model in order to check the behavior of our structure also by ambient vibration measuring. So we have a 5-story structure, a frame structure, which is plan irregular, elevation irregular just a little bit. Let's say it's at the border of the National Seismic Code. It means it has a setback from the ground floor to the upper floors. But due to the fact that this setback is about 30%, that it affects only one floor, we considered and decided not to take into account elevation irregularity and not to drop the behavior factor according to the seismic code. Like this, it was also designed. So this structure was designed like this. And we checked this assumption by pushover analysis. Okay, now the same layout I have shown you was investigated by 2 design approaches. First, by capacity design. Like this, the structure was designed actually, and it's functional today. And an alternative design was done by considering base isolation. As you can see here from this table, not much difference regarding the reinforced concrete dimensions of the elements was taken into account due to the fact that those measures come out of stiffness criteria, but the reinforcement ratios in those elements dropped quite highly. So we had, let's say, 60% reinforcement ratio drop in beams, up to 40% in columns, from the capacity design to the base isolated situation. Both structures are supported by a foundation slab, and the base isolated structure has a foundation beam girder that supports the superstructure and is laid on the isolation level, and the isolation level is supported by the foundation slab. It was considered that this foundation beam girder is more economically than doubling the foundation slab. Designed by two softwares was considered. First, model analysis by Rita software in order to check the structural performance, in order to check the structural design, and structural performance was investigated by static and dynamic nonlinear analysis using Perform software. Okay, point hinges for beams and columns and fiber sections for walls were taken into account. The isolators considered are, let's say, the state of the art at this point, and they are double curved friction pendulums. The behavior of those pendulums is given by such a diagram that gives you the relation between force and displacement. They were designed for 64 centimeters displacement capacity, considering the Eurocode 8 considerations, in order to have a little bit of comparison with other areas, seismic areas, where such pendulums are used. The Romanian National Code doesn't provide this maximum earthquake because we have a less return period. Okay, those are the eigenmodes for the structure. As you can see, for the first two eigenmodes, we have a coupling between translation and torsion in x direction, so the short direction of the structure. This coupling is actually considered to be explained by the position of the elevator shaft, because it's down at one edge at one side of the structure. And in y direction, the coupling is probably due to the rectangular shape of the structure. Now, first attempt to check performance was by pushover analysis. As I said before, here we have two diagrams which show the base shear force relation compared to the top displacement and the top rotation. With the green line, the vertical green line on the left side of the screen gives the design situation, and it shows, pushover curve shows that we have actually a structure which was designed according to the seismic code, which is valid today also, and nevertheless it has an overstrength of 3. So in forces, the force capacity of this structure is 3 times larger than the demand, actually. So we have a structure for which displacement demand is not the correct, the target displacement is not the correct tool to explain performance. Okay. Next, dynamic nonlinear analysis was performed, considering natural as well as artificial seismic records. On this slide, I want to show you the structural rotations. On the left side, we have structural rotations for the non-isolated structure, and on the right side, we have structural rotations for the isolated structures on top of both structures, and for the isolated one also at isolation level, to see what happens. What we may see by base isolation, the peaks are more rare, so the movement of the structure is delayed. We have less rotation amplification at the last floor, and we have a drop after the main peak. Some other results, considering dynamic nonlinear analysis, are displacements in the center of mass and along the perimeter of the structure. Also for the non-isolated structure on the left side and for the isolated one on the right side. We have here x direction, so input, seismic input in x direction and movement in x direction. And we see actually the same. The behavior and the movement of the structure is more smooth. Most of the, let's say 35% of the movement takes place at isolation level, and the rest of it is a rigid bodied movement. So it's a movement that gives no deformation inside the structure and causes no damage. The same thing we have done for the Y direction in order to check a little bit the torsional amplification. So we have seismic input in X direction, and we measure or we look at displacement in Y direction, so perpendicular to it, for the other main direction of the structure. And we may observe that actually we have displacement amplification. The percentages are not quite large, but the good news is they take place as well as for the X direction at isolation level. One curious thing is the fact that maximum displacements change place. So for the non-isolated structure, they come up at the flexible side of the structure, and for the isolated one, at the stiff side of the structure. Some main conclusions regarding this study. First of all, let's say base isolation doesn't correct plan irregularity, but it neutralizes its effects by concentrating the deformations at isolation level or by giving a rigid body movement supplementary to this isolation level deformation. Both of them give us no damage, so we come forward to our goal to have operational buildings after a strong seismic event. One, and my last explanation would be the fact that by base isolation, reduction of the maximum force, seismic force that acts on our structure of 0.7 was obtained. During design, a behavior factor of 6.75 was considered. So actually we may say both attempts give us the same in terms of reducing seismic forces. The major difference is the fact that for the non-isolated structure, those seismic forces which remain to be taken over by the structure produce damage, and for the isolated one, not. Thanks a lot for your attention.
Thank you, Professor Kober, Dietlinde. So, are there any questions?
Yes, Professor Oren Lovan is asking.
Oren, okay.
Yes.
Oren, please go ahead.
Thank you, Dietlinde, for the interesting presentation and actually interesting results. Just a small note, I don't know what the period of the isolated structure is, but know that the Eurocode's spectrum has the second corner period between the constant velocity and the constant displacement at a relatively small period of 2 seconds. I don't know about the true behavior of earthquakes in Bucharest, but for practical design using base isolation, I would be very cautious using this spectrum, because a small change in the second corner period may lead to very different results.
Yes, it's true. So our structure was, or let's say a little bit a step back, the isolation devices were designed for a period of 4.4. The base isolated structure came out with somehow 3.2 seconds first eigen period. So it was an enlargement, but this enlargement, considering our Romanian seismic code response spectrum, gives us just a shift of, let's say, 1.6, 1.8 seconds compared to the maximum to TC, to the corner period which ends the maximum response span. So that was also our goal, or our question: can we use efficiently base isolation under those conditions, or should we leave it? Thank
Okay.
you.
Thank you, Dietlinde. I think we don't have any more questions. We are a bit late, but we started late. So, okay. Third paper in this session is entitled Seismic Capacity of Eurocode 8 compliant RC frames with irregular vertical distribution of stiffness. The paper will be presented by Francesca Barbagallo.
Yes,
from
here I
University
am.
of Catania.
Good morning. Can you hear me?
Yes, yes, yes.
Okay, so thank you. Good morning, everyone. My name is Francesca Barbagallo from University of Catania, and today I'd like to show you our research regarding the seismic capacity of Eurocode 8 compliant RC frames, considering the influence of irregular vertical distribution of stiffness. The presentation, we should go ahead. Okay, so the presentation will develop into 5 parts. I will briefly explain the background and the methodology that was adopted. Then I'll explain how we designed the case study frames in the seismic assessment, and I will try to draw some conclusions. So starting from the background, we are all aware that structural regularity in plan and elevation is one of the key steps for designing new structures. And indeed, Eurocode 8 states that uniformity in the development of structure along height is important to avoid sensitive zones, damage concentration, and premature collapses. So we would expect that most of the new design structures are regular. Actually, according to a recent survey conducted by Professor Gersi, and including more than 2,400 buildings spread all over Italy, we found that more than 70% of new design buildings are classified as irregular. So to understand the reason why, let's try to have a look at this very simple example. This frame is representative of an RC frame, and it should be the prototype of regular structures. It has equal cross sections of columns and beams at all stories, regular interstory height, and it was designed according to code requirements. So we would expect that it's a structure, a regular structure, but actually it is not. So to understand what's wrong with that building, we looked at seismic codes and we found that basically they all share the same fundamental idea, that is, lateral stiffness has to change gradually from story to the upper one, and in case of irregular structures, penalties are introduced in design. Actually, Eurocode 8 states that lateral stiffness of regular structure must be constant along the height, or at most it must reduce gradually from base to top, while the Italian Seismic Code quantifies the limit of variation on lateral stiffness, and it says that for regular structure, the lateral stiffness must not decrease more than 30% or increase more than 10% from a story to the upper one. So this is the reason why that building is not regular, because the deep foundation beam increases the lateral stiffness of the first story more than 50% compared to the second story. So the prescriptions of code comes from different studies. The first studies date back to 1960s and 1990s, and they were mainly focused on understanding if the irregular structures could be assessed by lateral force analysis or if response spectrum model analysis was needed. But they basically use the shear type frames, so very simple numerical models. These studies developed also in the 21st century, but they mainly moved the focus from the linear to the nonlinear range of behavior, trying to understand the effectiveness of nonlinear static procedure in evaluating the response of irregular structures. But they were not actually interested in evaluating the real impact of irregularity on the structural response. So moving from this motivation, our methodology started from collecting a set of RC framed structures, including regular and irregular buildings, which were designed following seismic code prescriptions and assessed by nonlinear static analysis. The goal was to evaluate if and how much the seismic performance of the structures could be influenced by vertical irregularity. So the design case study frames shared the same geometrical features and included columns orientated with strong and weak axes, deep beam and flat beams, and different entity or gravity loads resting on beams. To extend the number of case studies, we varied also the number of stories, the length of the beam span, the height of the cross sections of deep beam, and the regular structures were obtained by considering a rate of variation of lateral stiffness from bottom to top equal to 0%, 10%, or 20%, where the rate of variation was evaluated as the difference of stiffness of the lower frame and the top frame divided by the lateral stiffness of the lower frame. From the regular case studies, the irregular ones were derived by changing the rate of variation of lateral stiffness, and we obtained 4 types of irregular case studies. A, where the stiffness reduced from first to second story. B, the stiffness reduced from the bottom to the top part of the building. C, where the stiffness reduced at an intermediate story. And W, where the stiffness increased from the first to the second story. All the regular and irregular case studies were designed by model response spectrum analysis according to the capacity design principles and in compliance with the requirements for reinforcement. Each frame was designed assuming 4 values of the behavior factor Q to attain high and low ductility structures, and we attained more than 54 regular frames and 810 irregular frames. All the case study frames were modeled as a nonlinear, as a bidimensional numerical model with beam elements using concentrated elastic perfectly plastic hinges, and they were assessed by nonlinear static analysis. The displacement demand was evaluated and associated to the corresponding peak ground acceleration using the N2 method. The seismic performance of the structures was determined in terms of shear failure, which actually didn't occur in our structures, so we will not use in the following. And also we evaluated in terms of plastic rotation of member end. To this end, we evaluated the plastic rotation capacity from the chord rotation, evaluated according to the equation provided by Eurocode 8, and we compare with the plastic rotation demand determined by pushover analysis. The ratio of the plastic rotation demand to capacity gave birth to the damage parameter D, which was equal to 1 when the significant damage limit state was attained. And we adopted 2 response parameters. The first one was the average damage attained at the significant damage limit state for beams and columns, while the second one was the PGA that corresponded to the attainment of the significant damage limit state in beams and columns. So here I'll show the results for the case A with 7 stories designed with behavior factor 5.85. On the y-axis, we have the rate of variation of lateral stiffness. On the y-axis, instead, we have the average damage in columns and beams. So basically, we can see that the average damage is concentrated in beams rather than in columns. The trend line shows that basically the damage in columns tends to decrease until a rate of variation of delta K lower than 40%. And basically, the damage attained in regular structures is quite similar to that attained in regular structures. We have also plotted the peak ground acceleration corresponding to the attainment of the significant damage limit states in columns and beams. And we can see that most of the cases were able to attain the significant damage limit state for peak ground acceleration larger than the reference value. Beams, however, attained a significant damage limit state for a peak ground acceleration lower than columns, and however, there was also a slight reduction of damage for delta K larger than 60%. The trend lines were also plotted for all the case studies, considering all the possible value of the behavior factors adopted and considering the minimum value of peak ground acceleration between columns and beams, peak ground acceleration corresponding always to the attainment of a significant damage limit state. We plotted the trend lines for 7-story case study frames and for the 4-story case study frames. And we can see that basically the increase of vertical irregularity does not affect the structural capacity because regardless of the entity of delta K, the structures are able to attain the peak ground, the significant damage limit state with peak ground acceleration larger than the reference value. So moving on to case B, basically the results are the same obtained for case A, so average damage concentrated in beams, peak ground acceleration corresponding to significant damage limit state was larger than the reference value, and the trend lines show that the capacity of the structure is not affected by the increase of vertical irregularity. Moving on to case C, the results are consistent with case A and case B. The only difference is that in this case, in case of very strong irregularity, damage in columns becomes not negligible. However, the peak ground acceleration corresponding to significant damage limit state is once again larger than the reference value. And for this case studies with 7 stories, the increase of vertical irregularity did not affect the structural capacity. A slight different result was obtained with the 4 stories, where the seismic capacity slightly reduced with larger irregularity, but however, it was always well verified. A different result was obtained instead in case of frames W, where I would remind you that the stiffness increases, so it does not decrease, but increase from first to second story. And here the damage is concentrated in beams, but reduces with the rate of stiffness variation almost linearly, while the damage in columns increases with the variation of lateral stiffness. This means that for large values of delta K, which means for irregular structures, the plastic rotation capacity is mainly attained in columns, and the peak ground acceleration corresponding to the significant damage limit state decreases almost linearly with irregularity. The trend lines show this result and show that the vertical irregularity in this case has affected the structural capacity. So maybe the reduction of the behavior factor that was here adopted was not working very well. So in conclusion, we can say that for case A, B, or C, the seismic capacity was basically independent from the variation of stiffness along the height, which means that the design criteria provided by codes are able to ensure a good seismic capacity even in case of abrupt reduction of lateral stiffness. So we would say that it seems quite restrictive to classify structures with stiffness reduction as irregular, even though avoiding abrupt reduction is always a good suggestion. Instead, it's important to note that the increase of lateral stiffness along the height had a strong influence on the seismic response of structures because it led to a larger concentration of damage and the lower values of peak ground acceleration leading to the significant damage limit state. So maybe in this case, the reduction of the behavior factor should be evaluated and related to the rate of variation of lateral stiffness. Of course, these results are first preliminary investigations, and further studies are in progress using more realistic numerical models with distributed plasticity members and running nonlinear dynamic analysis with a goal to verify if the results here presented are confirmed, and in case, how much. So thank you for your kind attention.
Thank you, Francesca. Are there any questions? I have a comment. I
have one question if possible.
Professor Rita Bento wants to make a question.
Who, Professor?
Rita, myself, Rita.
Rita, go ahead, please.
Okay, nice to see you, Francesca. Very nice
Nice
presentation
to see you again. Thank you.
and very nice work. Very clear figures, so everything very, very clear.
Thank you.
Just came on my mind, and in light with the keynote lecture, that I was looking for your results, your main conclusions. My question is, have you considered infields in your numerical models, and how do you think it could be your results different if you have considered or not? So it depends, of course, of
Yeah.
your present. Yeah, something that I remind based on the comments of Professor Varun.
Yes, so thank you for your question. Actually, we did not consider the infield panels themselves, but we considered the possible rate of variation that the presence of infield panels can cause in a building. So, for example, in case W, where we have the stiffness that increase from the first to the second story, well, that should be the case where we miss the infield panels in the first story and we have in the upper stories. So even if the infield panels are not directly modeled in our numerical model, however, their effect in terms of stiffness variation is somehow considered among those case studies that we have considered. So in somehow, maybe in a simplified way, however, we consider their possible influence.
Okay, thank you.
Thank you.
I have a comment in the sense that I believe really that this paper is further proof that seismic code specification for irregular buildings, starting from criteria to identify irregular buildings, are in need of improvement, and they must be based on background studies that, such as the one presented by Francesca, that really investigate the main parameters that play a role. Sometimes these values that are in the code are based more on engineering judgment than on some, at least they appear to be based more on engineering judgment than on some scientific background studies. So I think that we will discuss a little bit this also in the final session of our workshop. And okay, so thank you again, Francesca.
Thank you for the comments.
And, let's go to the final, last but not least paper, rotational seismic effects on irregular in elevation buildings. The paper will be presented by Professor Bonkowski of the Opole University of Technology.
Good afternoon. Today I'd like to show you our latest results on the rotational research that we do in Opole University of Technology. Okay. Firstly, I'll make some introduction to seismic rotational effects and our search to strong 6DOF records. I present some highlights from our earlier rotational research on our earlier rotational effects on building structures. And I'll show you our latest results on the response of the tall reinforced concrete building, first high, with, and without vertical irregularities in the sense of the soft story. And there will be also remarks and conclusions. To begin with, I have to say something about rotational ground motion. As traditionally in the seismic engineering, we use to mostly to realize structures induced by two horizontal seismic components. Sometimes we also use the vertical components, like for bridges, but we also know that the ground motion also include the rotational components. So we have one rotation about the vertical axis, which introduce torsion, and two rotations about the horizontal axis, which introduce additional rocking in the building. And I will focus on the later two. And in our research, the key problem is how rotational component, rocking of an earthquake, interacts with horizontal translational component in the same plane. If you have translational rotational 6D of record, and with, which is important, the plus minus signs of respective components properly assigned during the recording of the earthquake, we can perform time history analysis using non-discrete formulation of the equation of motion, when on the left side we have a mirror mass damping and stiffness matrix, and on the right side we have ground translational acceleration connected with the influence vector, which is filled with ones. And we have additional ground rotational acceleration with influence vector, which in that case is connected with the elevations of the respective degrees of freedom. But first, before we conduct any time history analysis, we have to answer if there are many strong 6DOF records to actually work with. And we have done some research on that matter, and we found out that the earliest strong 6DOF record can be attributed to Nigor, who in 1994 acquired ground rotations from a strong distance explosion using 1 kilotons of explosives. Another strong ground rocking was acquired by Takeo, but in that case we are not so sure about the correct plus minus signs of the respective components assigned. And we have also indirectly recorded rotations by Grazier. And recently, in 2017, Zembaty and others recorded intensive induced mining tremors. And at the beginning of our research, we used these induced mining tremors records to analyze what was the effect on the 160 meters reinforced concrete industrial chimney, and we have found out that this rocking component can have up to 65% contribution in the total response of the RC chimney. Also, if we change the signs of the rocking component, it resulted into up to 120% change in the overall seismic response. So the correct sign convention during the recording of the earthquake is really important. Luckily, but this previous recording was for induced mining tremors or for explosion, but we still didn't have the records for strong or more intensive earthquakes. Luckily, recently Perrin and others in 2018 recorded strong aftershocks in Greece. They started in 2014 a program for acquiring seismic ground rotation at Kefalonia Island in Greece during a post-seismic survey. They recorded over 960 of records with proper set plus minus sign components for all 6 components of the ground motion. The most intensive record has the modified Mercalli intensity 7, and in our opinion can be regarded as a long expected CDF record benchmark for the engineering purposes. This record was recorded by electrochemical rotational sensor R1 by ENTEC. Mostly all known by us strong motion records, rotational records was this recorded by this sensor for now. So we have taken, we analyzed the most intensive records. The most intensive record had the magnitude 5 and the peak ground acceleration over 4 meters per square second, and modified Mercalli intensity 7. Firstly, we calculated the response spectra for translational and horizontal, translational and rotational components. For the rotational component, we had to design special rotational single degree of freedom system. Then we have made some parametric analysis to check the rocking influence, which is the relative additional structural response between structures subjected to translational rotational ground motion and translational motion only. And this rocking influence can be presented on the 3D plane, where on the horizontal axis we have the natural period of the single degree of freedom system, and on the vertical axis we have the height of the single degree of freedom system. As the higher the structure is, the more contribution will have the rocking component. And on the color map, we have the rotational influence. Of course, there is some connection between the height of the structure and between the height of the structure and the period, natural period of the structure. And this typical relation is shown with the bold black lines. For example, this dashed black line is a typical relation between the height and natural period for concrete moment resisting frames. And it can be seen that if we have 100-meter high concrete moment resisting frame, the rotational component contribution influence can reach up to 50% in the total seismic response. So we later will analyze the response of the total reinforced concrete building, 30-story high, over 100-meter total height of the structure. The structure was regular in plane. And for this selected record, we calculated the storey sheets along the height and base, shear base overturning moment, and deep displacements. And we found out that the rotational component have over 15% influence on the selected components of the response. Of course, for the different motion that we analyzed, the total influence was also different. It could be also larger than 20%. And to analyze the influence of the vertical irregularities, we introduced the rowing soft story, which was introduced by changing the height of the selected story, and we the reference building has the 3.8-meter high each story, and the vertical irregular buildings have the 7-meter high story on the first, 11, 21st, and 30th floor. Firstly, we performed model analysis for the reference and vertical irregular buildings. And we can see that the change in the mode vectors and natural periods is not very visible. The change in the natural periods was less than 10% for the vertical irregular buildings. And then we analyze storey shear force. We analyze, here we can see the effect of the rotational component only, for translational component only, and if we analyze joint translations and rotations effects on the storey shear forces. So we can see that the irregularities cause slightly increase of the storey shear force when we analyze building influenced by the rotational component. This increase can be visible only in the higher part of the building. This cannot be seen for if we analyze building with the translational component, or when we analyze the building with the translation, when building influenced by translational and rotational component jointly. Then we repeated the same procedure for the analyzing of the interstory rift. The conclusion can be the same. The rotational component increased the interstory drift at the higher parts, but didn't have any influence when the building was influenced only by the translational component, or when it was excited by translational and rotation component jointly. Of course, in this case of this record, the rotations didn't have small effects on the response of the building. So we also checked what would be the effect of the rotations if we artificially increase their intensity. In this case, we multiplied the rotation effect by 5 times. And firstly, we assume that we will have the most change in the interstory drift at the higher parts. But after our analysis, we have seen that the change of the interstory drift at the high parts was still neutral, but we have some change in the lower parts of the building. So we can say that the interaction of rotational and translational excitations can give totally unexpected results. So still more we have to analyze on the bigger data sets, for example, more rotation translational records. To sum up, we performed comprehensive analysis of the seismic signal, including response spectrum analysis in time and frequency domain, using intensive 6DOF records from the Kefalonia Island in Greece. A special displacement response spectrum was defined to study joint horizontal rocking effects on the seismic response. As you can see, the rotational ground motions shouldn't be disregarded in the analysis of the tall structures. We analyzed the case of the storey rowing along the height of the building and the vertical irregularities caused by the increase of storey shear force and interstory drift in the upper part of the building induced by the rotational excitations. But still, more research is still needed for different types of buildings and using nonlinear analysis. Thank you.
Thank you, Piotr. Is there any questions?
Again, no questions from the participants on the conference.
Are there any questions?
Well, I can make one question. Yes.
Okay. Please go ahead.
So it's true regarding the results that this effect should be considered, especially for tall buildings. But how exactly do you propose this to be considered in order to add a line to the present code? How this can be achieved? But
actually, the Eurocode 8 part 6 have the rotational response spectrum, but when we compared this rotational spectrum from the Eurocode and the actual rotational response spectra of the recorded earthquake records, we don't have a good match between these two. So we still have to wait for more translational rotational records to actually make this rotation spectrum in the Eurocode better. So we are only at the beginning of the work right now. But I know that there are right now more rotational sensors developed using optical fibers. So maybe in the few years we will be able to make our Eurocode better.
So we need to improve the database collection, and
yes,
it's difficult on this specific case.
So thank you. And this issue of rotational seismic input is a more recent one. We started looking at it in Opole in 2014. There was a special session on it, so it's important to continue research in this field. And okay, so I think we can finish this session. We are 20 minutes late with respect to the schedule. So thank you to all speakers for very interesting presentations and to co-authors. And so Rita, what time should we start again?
I would suggest same time, a short lunch, not to get too late. What do you think? So I probably, if it is okay for all of you, I will propose trying to start at 2 p.m. Lisbon time. So we have about 45 minutes to have lunch.
Okay.
Do you agree? Yeah.
Especially the chairs and the speakers of next session. I think that everybody agrees. Maybe I don't see.
No comments?
No comments.
Okay, so we'll do our best to start on time. Okay, thank you so much for participation.
Very good, and see you later. Okay.
Thank you.